Today's lesson is on 2.4, Reasoning with Properties of Algebra. So this is where we start to get into writing proofs. And we're starting with algebra because you're all familiar with algebra and you know how to manipulate algebra and think logically, although you've probably not thought through solving algebra problems quite like you're going to be asked to solve them in this section. So before we get started with actually writing proofs, we need to identify some properties. These are properties that you've seen before, you know how to do them, but now we're putting a name with them so that when we write our two-column proofs, we can identify each step and we can defend each step that we're doing to solve. So the first one is the addition property, and basically that says that you can add the same number to both sides of an equal sign and it remains the same. So if we have A equals B, then we can add C to both sides and it remains the same. The subtraction property is next. It's just like the addition property, except for we can take something away from both sides of an equal sign and it will still remain equal. Multiplication property, similar. We can multiply both sides of an equal sign and they will remain equal. And then division, divide both sides of an equal sign and they will remain equal. Reflexive property seems silly, but it says for any real number, A, it equals itself. So that sounds silly, but it's necessary. We're going to need that. So basically, if we have something equal to itself, that's using the reflexive property. The symmetric property basically says that if we have A equals B, then B equals A. So we can reflect those similar to a reflection in a mirror, and they are the exact same. I'm sorry, the symmetric property. They're symmetrical. They're the same going forward and backwards. So if you have x equals 3, that's the same thing as 3 equals x. You've known that for years. The transitive property says if A equals B and B equals C, then A equals C. So that sounds a little bit like those logical reasoning, deductive and inductive reasoning we talked about yesterday. So if A equals B and B equals C, then A equals C. The last one that we're going to look at is the substitution property. And that basically says that if we have two things that are equal, we can substitute it in for the other. So if I know that x equals 5 and I'm solving a system of equations, you can put 5 in place of x in that system to solve it. So again, all of these should pretty much be familiar to you. All right, so let's look at our first example. Now, because it's a two-column proof, we make our two columns. On the left side, we write our statements. What is it that we're doing? And the right side, why are we doing it? Sounds a lot like our extended response problems or our POWs that we write, or that you were writing back in 6th and 7th grade when you did the what I did and why I did it part. That's in preparation for this. So we have 3x plus 12 equals 8x minus 18. So we write the statement and we rewrite that equation, and our reason is that it's given to us. I always start two-column proofs with the given statements. Then the next thing we're going to do, and the way I solved it, was to add 18 to both sides. You could do a number of different things, but I started with adding 18 to both sides. So then my next line of the equation is 3x plus 30 equals 8x. How did I get to that? I used the addition property of equality because I added the same thing to both sides of the equation. Then my next step was to subtract 3x from both sides. And so the next line of my problem is 30 equals 5x. How did I get that? I used the subtraction property of equality. Then finally, I used the division property of equality and divided both sides by 5 in order to get 6 equals x. Now you can leave it that way, or you could use the symmetric property and write x equals 6. And you would have to then state your reason being the symmetric property. Or you can just leave it as 6 equals x. I am fine with that as well. Let's look at another example. This next example is using a formula, and it's hopefully one that you've seen and worked with before, and that is the Celsius to Fahrenheit formula. So Celsius equals 5/9 times Fahrenheit minus 32 degrees. So I want to solve that formula for F. So I want to rewrite it so F equals. So I start with my given statement. Then I'm going to multiply both sides by 9/5 in order to get rid of the 5/9 on the right. The property that allows me to multiply both sides of an equation is called the multiplication property of equality. So then my next step after my given is to have 9/5 times C equals F minus 32. Then I'm going to add 32 to both sides using the addition property of equality, and I get 9/5 C plus 32 equals F. So again, we're using these formulas and equations to solve. Now, we have properties of equality that are used in geometry, and the reflexive, symmetric, and transitive property are all used in geometry. So not only do they work for algebraic equations, but they also work for geometric proofs as well. They're the same thing, except for instead of talking about a number equals a variable or two variables equal to each other, we're talking about segments or angle measurements. So the reflexive property, line segment AB equals line segment AB, or the measure of angle A equals the measure of angle A. The symmetric property says that if AB equals CD, then CD equals AB. So again, with line segments, we can flip them around. Same with angle measurements. The transitive property of segment AB equals segment CD and segment CD equals segment EF, then segment AB equals segment EF. Same is true with our angles as well. All right, last example. This one is about geometry. So we want to verify that AB equals CD. So we're going to write a two-column proof. And so we start with our given. Our given is that AC equals BD. We know that. It's told to us. It's given to us. So then I know BC equals itself because of the reflexive property. So then I can subtract BC from AC and from BD. So I know that AC already equals BD. So these two I already know are equal from the step up here. And now I'm going to subtract the same thing from both sides using the subtraction property of equality. So then I'm left with AB plus BC equals AC. That's using the segment addition postulate. So we know that that's true. We also know that BC plus CD equals BD. Again, the segment addition postulate. And those you can combine into one step if you'd like, or do them as two separate steps. Then I can say that AB equals AC minus BC. How can I say that? Well, if I look up here, okay, I have AB equals AC minus BC. So here's AC minus BC equals BD minus BC. And then if I say CD equals BD minus BC. So that's using the subtraction property of equality. So AB, which is right here, plus BC equals AC, I'm subtracting this BC from both sides. And so it's gone from this side and it's over here. So I'm taking this and I'm subtracting BC from both sides. I'm doing the same thing here, subtracting BC from this side of the equation as well as from that side of the equation. Hopefully you see that. Then that leaves, because now I have AB equals AC minus BC, and CD equals BD minus BC. But if you look up here, these two are equal to each other from up here, so then they can be substituted. These two can be substituted in its place. Take a minute and look